Welcome to the course on computer design of electrical machines. We will have a lecture 3 today on equivalent circuit approach for the design of electrical machines, which are used for different parts of the design of these electrical machines. So, with this outline, we would like to introduce, of course, this topic. Then we will go to magnetic system and material, and construction of magnetic equivalent circuit, then nonlinearity, typically springing and leakage flux in magnetic circuit, and thermal equivalent circuit, and followed by numerical problems with references like. So, coming as an introduction to this topic, we say the magnetic and thermal equivalent circuit are essential tools in the design and analysis and optimization of magnetic and thermal circuit in addition to electrical circuit. And these complex systems can be analyzed using equivalent circuits that are widely used across applications from power electronics and electrical machine to electromagnetics and thermal capability. And as a research material, as you can see with a couple of examples of the typically of equivalent circuit of a machine of with the magnetic circuit and with the typically of your thermal circuit. So, this is in addition to electrical circuit. Electrical circuit, of course, we were covering a lot typically in the electrical machine design, but these, especially the two, magnetic circuit calculation and thermal circuit calculation, we were taking very, you can call it like very empirical relation. Now, we can go reasonably accurate calculation with these equivalent circuit compared to there was like a big embargo in the two. Either we were taking very lump parameter approach for these two topic, or we were going very deep like finite element analysis. So, this has given a inbuilt approach, this equivalent circuit approach for the two circuit, especially magnetic circuit and thermal circuit. So, now coming to equivalent circuit modeling in computational is less demanding and faster than finite element analysis. So, equivalent circuit modeling is commonly used in electrical engineering for analyzing electrical circuits, typically for transformer and electronics component, and thermal engineering in analyzing the heat transfer for thermal system and network like. So, this is the typical examples that if we have a for magnetic circuit, a toroidal shaped magnetic core with the air gap. So, we can define the typically a magnetic circuit for that, and then another equivalent circuit of thermal heat flow. Typically, you can see in the heat sink from the analyzing equivalent to a thermal equivalent circuit, like for the heat flow. So, these are two important, you can call it the, we just give a circuit analogy approach for these two, you can call it the parts of the electrical machines like. So, if we look into typically equivalent circuit relation between this, because you want most of the people understand the electrical circuit, but of course, we can say here the magnetic circuit as well as thermal circuit. There is a commonality that there is a, you can call it the driving force, or you can call it the excitation source for electrical circuit is normally the electrical we can call it the voltage, but in case of magnetic circuit we call it this as excitation, and we denote it magnetic intensity also, that is number of turns and current equivalent to H, and the unit is ampere per turn. And similarly in thermal circuit, of course, it is the losses in that. Then of course we have a flow which you call it in electrical circuit as a current, and in typically which is typically current density multiplied the area in a conductor. And in case of magnetic circuit, we have this the flux, which is the flux density multiplied the area. And similarly, we in the thermal circuit we have a typically how much is the heat flowing, and that is again the specific heat generation multiplied the area. Similarly, we have a resistive element which we represent as a resistance in electrical circuit, and we calculate it length of the conductor L upon mu A, where the mu is the resistivity of typically of the conductive material. Similarly, for magnetic circuit we have a reluctance, and in the typically thermal circuit also we represent as a kind of equivalent resistance like. Then the application of Ohm's law is your voltage equal to IR, especially current multiplied resistance. Similarly, magnetic circuit also the MF consumed is flux into reluctance, and similarly in case of thermal, this you can call it the losses proportional to the typically a flow of heat and multiplied the equivalent resistance of it also. So, there are some equivalence we have in all the three circuit like. Now, typical example here is, if you can say, for electrical machines field analysis, we call it finite element analysis of electrical machine showing the field line, but you can understand it takes a lot of computational power as well as the typically it takes a lot of time for computation. So, we cannot certainly do FE analysis for all the machines. We just conduct when the design is finalized to make sure that design is not have very excessive saturation in some part also, as well as the concentration of the flux is not at some corners or so. Otherwise, I mean, just to check whether the machine is quite successful after designing the approach, basic analytical approach also. Similarly, in case of heat flow, we do CFD, I mean, like force convention of the heat sink, how the heat flows through the typically in different parts into the environment, like from the heat generation. So these of course are the very, you can call it deep calculation required for, it's difficult for every design, but you can say we can use the magnetic circuit and thermal circuit with the some kind of in between approach with the lump parameter approach to the reasonably accurate approach, I mean, which applicable for large number of machines with reasonable accuracy like. So we can call it here the if we talk about electromagnetic design or magnetic circuit, the electromagnetic design is a critical aspect of designing efficient and reliable transformer and electric motors, and both transformer and motors rely on electromagnetic principle of to function, and careful design essential to optimize their performance. So you can just see an example electromagnetic analysis of motor geometry showing the flux density variation, I mean, in different parts as a bar chart, which comes as a output of the typically you can call it of FEM analysis, and you can see what is the maximum flux density, where the concentration of the flux is there in a small area with the flux density maximum of 1.825 Tesla and the average flux density of 1.53 Tesla. Then of course, this is typically a magnetic equivalent circuit of permanent brushless DC motor with the dual rotor structure, where we have a, I mean, equivalent excitation of the flux produced by the magnets, and then the reluctance path of different parts in the typically in the rotor core, then the rotor, you can call it like a, I mean, the other parts of the rotor followed by air gap, and then in the typically on the rotor. So it gives you a clear complete magnetic circuit, I mean, the path with the even excitation and reluctances like. Similarly, you can just see this is another equivalent for of magnetic circuit, equivalent circuit approach for the reluctance motor. How really a different reluctance and excitation. The excitation comes from the winding when we excite it is shown here, and then we have reluctance of different parts, reluctance of the pole, reluctance of the stator core, reluctance of the typically of your rotor pole, and reluctance of the typically coming out of the rotor core also like. So that complete the magnetic circuit of the your typically or magnetic circuit equivalent of the your reluctance motor. These are typical examples, and there are these are the further example. If you look into the typically a surface mounted synchronous motor, permanent synchronous motor, and how it is the actual physical geometry with the conductors and the magnet placed on the surface of the rotor, how the flux line flows into different parts, even you can measure the flux outside the typically of stator core, and how is the equivalent of it. So certainly the magnet equivalent we put as a Hall magnet here as a excitation for the flux with the parallel reluctance, and then we have a reluctance of different path. So we have certainly, I mean, account for every flux of the magnet, I mean, the you can say reluctance of the in a part of the magnet, then air gap, then we have a reluctance corresponding to stator, and as well as the typically going the flux corresponding to even the leakage flux, which or we call it stray flux also, and effective calculation corresponding to this equivalent circuit. So this approach of equivalent circuit give reasonably good approach compared to even compared to the lump parameter approach. So this becomes a now new tool for the designing of these machines that we can use the for this magnetic circuit calculation very quickly from this equivalent circuit approach like. Then we have another equivalent circuit approach for this typically of this motor, where we have a flux barrier and we have a concentrated winding on the stator of typically of this motor. So if you look into equivalent circuit here of this interior permanent synchronous motor, where in flux barrier we put the magnet, I mean, and you can call it the excitation due to the typically of stator winding, excitation due to permanent, and then we have a typically the reluctance of different parts like also. So it gives again the reasonable good accurate equivalent calculation of the this interior permanent typically synchronous motor, I mean, which are used probably plenty of application, which I mentioned even for typically of electric application. So this is a equivalent circuit correspond to that motor like. Then we have equivalent circuit typically of typically synchronous machine, where we have a silent pole structure, I mean, of the on the rotor, and we have a different parts on the similar to conventional AC motors. I mean, so we have a typically you can call it the reluctance of the stator core, stator teeth. Then you can have a even the with the saliency, and then we have a flux barriers on the rotor. So we have a reluctance of that. So this gives equivalent circuit of this of new synchronous reluctance motor with the new typical new geometry with the flux barrier in two-pole structure like. Then that is about typically of magnetic equivalent circuit. Now we coming to like a thermal design. And thermal design, of course, if you take a cross view of your three-phase squirrel cage induction motor, so we have a heat generation or an energy loss in the electrical circuit in winding. Then we have energy loss in magnetic circuit as a core losses, and then we have a heat loss certainly in mechanical parts, especially the typically the bearings and other parts as a friction. I mean, in the different mechanical parts or windage even like. So that is the how really the losses are, I mean, in different parts of this machine, and from these losses you can just see this is the thermal heat flow, how goes in this electrical machines with the from the heat flow from the winding, heat flow from the typically slot portion, and heat flow losses typically in stator cord and teeth, then in the goes to the frame, then it goes to ambient temperature outside and end shield. So this is all similar to for air, then air gap from then rotor side, the typically on rotor winding and portion, then rotor cover, then rotor end shield, then rotor end surface, and finally the bearing, then axial dust. So how the really conduction and convection and radiation and heat airflow is there in this typically in this typical electrical machine three-phase induction motor like. So now we can say, I mean, that was typically kind of equivalent. So now we can say traditionally in electrical motor design, the thermal design have received much less attention than electromagnetic design, but finite element and analysis and CFD software are starting to features including to make it easier to set up the electric motor thermal model. However, equivalent circuit modeling is computationally less demanding than the faster FEM analysis. So the result you can say how it is a animated tangent heat flow through the FEM like. But how we can have a really a thermal design, typically traditional motor sizing method, the sizing based on single parameter like thermal resistance, how heat, housing heat transfer coefficient, then winding current density and specific electric loading, followed by thermal data from simple rule of thumb with the current density and flux density typically, and test on existing motor and the computer catalog data, and how single parameter fails to describe the complex nature of motor cooling. And alternatives are typical analytical lumped circuit thermal analysis and numerical thermal analysis. As you can see from the body, you can have it like a thermal analysis. It depends like how you are going to take from the winding to the typically ambient temperature, the heat flow through thermal resistance like. Now coming to typically a numerical for thermal design, the numerical thermal analysis, first is this finite element approach used to accurately calculate the conduction heat transfer. As you can see here the diagram of finite element analysis and computational fluid dynamics. The simulation of fluid flow involved the solution of stat coupled nonlinear and second order partial differential equation. However, nowadays of course we have a typically a scanner, thermal scanner also for all these machines to get even the actual temperature distribution also, or image of the thermal temperature in the actual machine also like. So that's in light of that we have to really go more deep calculation. So coming to for thermal design, in order to determine the temperature distribution, a good estimate of losses have to be known, and property of the cooling property have to be known, and the thermal characteristic and property have to be known. So an optimized thermal design can help increase the machine rated, you can call it the rated power substantially. Like I mean, you can think about how really a properly optimized machine, and because it limits the typically the output power. I mean, so you can if you properly thermal design, then you can utilize the machine part more efficiently, and you can get optimum output from the machine. Like so, this is equivalent typically thermal estimation of interior permanent synchronous motor using thermal equivalent circuit as it is shown here. That we have a typically end cap air, and then we have different parts how the thermal resistance are shown and the loss distribution in different parts is shown as a P as a losses in different parts, including the magnets as well as the stator and winding and different parts. I mean the as a thermal equivalent circuit like of this magnet interior permanent synchronous machine, including the magnet in the interior body into that. Then the thermal characteristic of material is typically temperature dependency and temperature limits, and heat dissipation, thermal circuit and cooling, and thermal efficiency and cooling condition normal and force. So maximum allowing loading according to the thermal limits as the cooling capability. So you have to consider all these cooling conditions and thermal efficiency while you are really considering this thermal design. So you can look into how these different materials have thermal conductivity and typically the density of the material like aluminum alloy. Then we use laminated core pack as radial, then copper, permanganate, stainless steel, epoxy resin, varnish slot liner, and potting material. So these are certainly how different have a thermal conductivity. I mean the different parts. So and then density. So this help to even to make a thermal equivalent circuit properly, knowing the dimensions and then typically calculating the thermal conductivity and accordingly the resistance, thermal resistance of different parts to make a complete equivalent circuit of this with proper density, in the sense that with the density you can find out how much is the material and how much is the typically comes as a total resistance like also. And then this is the typically the data corresponding to different parts of it, I mean including the used in the machine as a part of mechanical parts which really responsible for thermal design like. Then coming to magnetic system and material. So this in magnetic circuit, magnetic system and material, the interaction between material and magnetic field primarily originate from the two main effects. The first effect can be attributed to the magnetic moment of the electron and it travels within its shell, and this can be somewhat simplicity envisioned at the moment generated by the electron or orbital motion, and the second effect emerges from the magnetic moment associated with the spin of electron. So you can just clearly see without the external excitation field, without the field excitation, how the geometry of typically of this dipole in the or magnetic domain with the magnetic moment is there, and once you apply the extra field, magnetic field, I mean the H on this piece of material, how the domain wall really, I mean react and how the magnetization direction really work out with these all magnetic dipoles like that. Then coming to typically the complexity of magnetic system comes with multiple materials which you are using in a different part of the machine, then varying permeability of these material. I mean, and the permeability changes with the excitation, especially in ferromagnetic material, and then the of course complex geometry typically which we call it like a maybe a flux barriers in some of the machine as we mentioned it in permanent machines like also, and putting the different kind of magnets like maybe rare magnet to put in flux barrier. So some of the challenges that engineers and designers face when analyzing and designing the magnetic system is the nonlinear magnetic behavior, then coupling effect, eddy current and losses, and hysteresis and memory effect, and frequency dependence like of these losses also. The advantage of magnetic equivalent circuit is it provides you simplified complex magnetic system. It simplifies complex magnetic system and speed up the design process, especially provide the insight for the optimization that you can use the quick calculation during the optimization if really you are using it a part of optimization, which FEM analysis is not typically possible, that you can do FEM analysis of every typically you can call it of the design like, because you are going during optimization probably billions of design and you are searching the best design based on the lump parameter approach. But this gives you reasonably accurate result to really help you out for getting a better design. So limitation traits are they may not be provide a highly accurate result for the complex and nonlinear system. And the analogy, of course, we already talked about in a table, but this is analogy between electrical magnetic circuit, which reported in, I mean, most of the references that you in electrical circuit, you have induced, you have a applied voltage, then you have a typically the resistance and the current flow through this when you apply. Similarly, in magnetic circuit, you apply the MF and the reluctance absorbed and the flux flows into the magnetic circuit. So typical example here of fundamental law of electrical magnetic circuit is that you can call it the total MF. I mean like you can calculate as a linear integral of this magnetic intensity with the typically the your distance of magnetic path, as you can say that you have a different MF consumed for different parts of the magnetic circuit F1, F2, F3, and this sum of F1, F2, F3, F4 is just equivalent to total excitation, because you have a single conductor and flowing through this which is responsible to, I mean to get the total excitation requirement of this, and I mean so turns is here 1 which equivalent to, and then the MF is equivalent to simply I with sum of all MF required for producing the field in this magnetic circuit. Then of course we can call it comparison of fundamental law of electrical magnetic circuit. Here we have a typically again the you can call it integral of flux density with the surface area, so that gives the total flux. Here also some of the total flux around the loop is 0, so it's a phi1 plus phi2 plus phi3 at a node is equal to 0. So it's just like apply as a typically as a current Kirchhoff's law. So similarly here we apply similar to in magnetic circuit as a your equivalent to, you can say Kirchhoff's law of the flux like. So you can call it here the relationship between the flux density and the field intensity can be captured in many different forms, and in absence of magnetic material the relation between B and H may be expressed as B equal to mu 0 H. So we consider if it is not a ferromagnetic material, this all materials behave similar to like air. So we take the permeability of the air mu 0 here. So mu 0 is the permeability of the free space having the value equal to 4 pi into 10 power minus 7 Henry per meter, and its SI unit is Henry per meter. So in magnetic material, the magnetic moment of the material and introduce another term referred as magnetization and has a unit Tesla. Well, in particular, the relation between B and H, you can call it B equal to mu 0 H plus M, and M is in ampere turns per, so that is typically you can call it equivalent. Then we can call it M equal to mu 0 X into M as a fractional part of, you can call it, of the typically of your here the part of flux density, where X is known as a susceptibility and it's a dimension, because it's a relative term. So the relation between B and H can also be written as B equal to mu 0 1 plus X into H, or B equal to mu 0 mu R H, and where mu R is the relative permeability, magnetic permeability that is relative to free space. So the relation between B and H can be written more in simply as a B equal to mu H, and where mu equal to mu into mu R is the total magnetic permeability. And to present the nonlinearity in a magnetic material, the permeability can represent as a function of field intensity and the flux density. So here you can call it B equal to mu H into H, or equal to B equal to mu B into H, like on. So, well, we can call it how typically as B and H are parallel, so that we may treat this quantity as a scalar. So the relationship between flux density and the field intensity is depicted in figure here, especially for most of the ferromagnetic material. It gives by like a BH loop, as it is shown here. We discussed in the previous topic. Also, you can say we start from 0 and we provide the excitation, go to maximum flux density correspond to maximum magnetizing force. But when we reduce it, it does not remain, it goes to 0. This ferromagnetic material have a we call it retentivity, we call it residual flux density, or we call it the typically the retentivity of the material. And then to reduce it to 0, apply the excitation in opposite direction to make it 0, and at which it goes to 0, we have to what the the magnetizing force we apply in opposite direction, we call it coercivity, and denoted by minus SC here. Then of course we can excite in opposite direction, so it goes to again maximum flux density minus B max, and then we again reduce excitation, so again we go to residual flux density in typically minus VR, similar to identical H plus VR, and then again we can apply the flux field in positive direction, and we come to again with the coercive force. So this complete complete cycle of BH curve, we call it BH loop, and this area of the loop beside the typically you can call it like one sense when you are having AC excitation in provide the losses in for one cycle, and if you are operating, let's say, the device for 50 Hz, so you have to multiply 50 Hz 50 times to get the complete hysteresis loss of the material. However, for as a typically this characteristic for the defining the the soft magnetic material, we consider that this loop size, this BH curve should be as small as possible, so that core loss are reduced. But when you are really going as a hard material to use as a permanent, we don't expect that it will be going through alternating flux. So we want this area should be as large as possible, so that the energy density provided by this, it's quite large, like also. So we can call it because of the complexity of predicting or even describing the behavior of B and versus H characteristic, ignoring the hysteresis effect, a simple model is considered. And after the flux density B reaches a value of B max, the slope of the curve decreases markedly as material is said to be to saturate. And we can call it here in the PS characteristic simple sample of M7 silicon steel and corresponding permeability function normalized to permeability of free space as shown here. So we have a characteristic between B and H, how it goes. Then from this characteristic you can find out the typically relative permeability versus H. So as you can see, as we increase the excitation or we really have a saturation, the relative permeability reduces because of this saturation. Like also, and then of course we have a, you can call it the typically the especially related to the steel, how this relative permeability go to reduces to with the and goes to very small when really go to very high, typically the excitation along with the flux with respect to the flux density, like So for the construction of permeability function, the expression of flux density, that is B equal to mu 0 H plus M, is considered. The magnetization as a function of field density is given as a expression here. So MH equal to sine of H, and is dividing into a large number of steps, K equal to 1 to K, and MK H upon K and 1 plus h upon k. So we consider this part of saturation through this function of m. So where mk, hk and nk are the coefficient, and k represents the number of turns, and the sign function is defined as typically either 1 when x greater than 1, 0, and then equal to 0 when x equal to 0, and minus 1 when x is less than 1 or so, because of this geometry of the BH curve, like we do that way. The permittivity of function field intensity is given as a expression mu h equal to mu 0, again the function of k equal to 1 to summation of k equal to 1 to k mk upon hk into 1 upon 1 plus h upon k to power nk. So probability of function b is given as a mu b, that is mu 0 rb upon rb minus 1, where rb is the ratio of flux density to magnetization in Tesla, and function rb can be written as rb equal to mu r upon mu r minus 1 plus gb. Here mu r is a relative permeability in the magnetically linear region, and gb is the function that essentially 0 in the magnetic linear region, but eventually begins to rise nearly once the saturation starts in the material. So it accounts, you can call it, it accounts really the saturation in the, or to represent this, you can call it the saturation part of magnetic characteristic. So coming to now construction of the magnetic circuit equivalent. So you can consider that a piece of magnetic material, the flux going into the material is denoted phi a through the surface area SA with the MF drop of FA and the length LA, and the cross sectional area is A. Assuming that the field intensity is uniform, the MF drop across the material will be F equal to HA into LA, where HA is the field intensity in the indicated direction in the parallel to the material length LA. Now assuming that the flux density B is uniform and parallel with the surface SA and can be represented as a scalar BA whose direction is the same as the surface, the flux into the surface may be expressed as phi equal to BA, and the relation between the MF and the flux can be written in terms of reluctance, that RA a sample A on the flux tube A as the Ohm's law for the magnetic circuit F equal to RA into phi A. So now the relation between flux and MF can also be expressed in terms of permeance of sample A and has a unit of H and analogous to conductance, that flux phi A equal to PA into FA, where PA is the permeance, and where mu A is the permeability of the material, A also reluctance is analogous to electrical component resistance and has a unit 1 upon H. So your PA equal to A0 mu 0 upon LA, or reluctance is permeance and the reluctance is just the reciprocal of it, that is L upon divided by AA into mu A. So this is typical example of material effect permeability, how you really define with magnetic flux density with the magnetic, you can call it field strength for typically of the nonlinear portion and linear portion, and how we express the nonlinear portion especially with the apparent permeability as well as incremental permeability to express with, and then we have a typically here the B versus H for ferromagnetic material, and typically with the paramagnetics, then superconductor and vacuum, and typically the diamagnetic material. The some are nonlinear, especially for superconductor, it's a nonlinear as well as paramagnetic nonlinear, but paramagnetic, diamagnetic and vacuum, this is linear characteristic. But of course, you require large excitation, especially for typically even for the vacuum also. So now coming to magnetic circuit with different media, as you can see here, the magnetic circuit, you have a core and you have a air gap. So you have excitation which is consumed not only by paramagnetic part but also by the air gap. So we can say the flux density in core part or steel part is phi upon AC, that is flux density, and the flux density typically in case of air gap is phi upon AG, and that is in the flux density in air gap. You can call it, of course, there is a called typically the fringing. If the fringing is there, the flux is typically neglected, that is AG equal to AC, and therefore BG equal to BC, that is phi upon AC, considering that the same cross section area of air gap at your core. Now coming up, typically defining the inductance here, if you look into here the small air gap as it is shown here in the core, and you have a excitation by current for the number of turns and length of the magnetic circuit is shown in this. So this we can define the inductance here. Any coil wound on the material can be represented by ideal circuit element inductance, and inductance is defined as the flux linkage of the coil per ampere of in this. So usually this small air gap we put in the inductor so that the value of inductor is not changed even if there is a saturation in the core, because the majority of the MF is consumed by the air gap. Hardly, maybe because of depending upon the relative permeability, the ferromagnetic material consume very small excitation, the major excitation by air gap, So even with the saturation, the excitation requirement of ferromagnetic material may not change much. So we use this for typically the inductor use even for the DC circuit as well as the inductor, defining the inductor many electrical circuit even for the AC circuit. That is the basic concept how really we really design the inductor for typically of many circuits like that. So we can say flux linkage lambda equal to n phi, and inductance we can define lambda upon I, or L equal to n phi upon I, or NBI, or n mu HA upon I, and that we can call it say n mu HA divided by HL upon n, and it becomes like n square divided by L upon mu A. So, well, this is typically how we define the inductance. So this can be even defined as in L define n square upon reluctance, or it is also defined n square into permeability, permeance like common. So relative magnetic, the magnetic equivalent circuit is considered by the way of relative simple example of UI core, which normally we use either typically in the inductor of the or the transformer. So you have I portion, you have E portion. On E portion, usually we put you can call it the conductors, and you can see how typically the winding is put on this core, and this complete dimension of conducting material are given here. So G is the typically air gap on one side, and you have two air gap on both sides. Then you have winding depth, winding width, slot depth, then width of the I core, width of the end of U core, and width of the base. So from this, of course, you can find out the magnetic equivalent circuit, connect the nodes with the circuit element representing the reluctance between the nodes and representing MF source, and the reluctance is shown in figure here. I mean, so where if you consider Ri is the reluctance of I core, RBC is the reluctance of UB core, and RLUC is the reluctance of lag of U core, and RG is the reluctance of air gap. So if you look into, you have excitation here, Ni is produced from the winding, and then you have the reluctance of different parts, including both the air gap as well as the reluctance of I portion and reluctance of the typically of U portion here. So this gives you a equivalent circuit, magnetic equivalent circuit for the calculation here. So now the reluctance Ri and RBUC and LUC are functions of flux because they correspond to magnetic nonlinear material, and Rg the constant corresponding to the linear magnetic, that is air. So you can calculate the different, I mean Ri, the all formula are given here. I mean Ws plus W upon Lwi for RIC, RBUC, LUC and Rg, and then of course you can find out what is MF required Fs equal to Ni, and you can say similarly similar to electrical circuit analogy, the sum of MF drops is equal to the MF, like Ni equal to R equivalent into phi, and where the R equivalent you can find out from this equivalent circuit, that is total reluctance will be RIC, that is in the I core, then your core, typically the core of your U type plus 2 air gap RULEC. So this gives you typically the total reluctance of the equivalent circuit. Now coming to numerical solution for magnetic circuit equivalent, the analysis of magnetic circuit is analogous to the solution of electrical circuit, and there are many analysis approaches that can be used when faced with the complicated magnetic circuit, and mesh analysis and nodal analysis are most conveniently applied. So now coming to numerical solution of this magnetic nodal analysis of magnetic circuit equivalent is based on Kirchhoff flux law, which states that the sum of the flux in every node must be equal to 0. So summation you can call it all the flux, typically I equal to Li up to j and minus Bij equal to 0. So using nodal analysis, the system is formed equation Pn Fn equal to phi, and where LPG is the list of all branches that node j as the positive node, and Lnj is the list of the all branches that have node j as a negative node. So now coming with the example of this magnetic circuit equivalent, so we have here solved this given circuit to determine the flux coming out of the MF. Therein in the two non-zero node potential and 5 branches, the 4 branches are all permeance is B I1 equal to 2H, B2 equal to 4H, and B3 is the 5H, and B4 is the 6H, and the 5th branch of MMF source is FS5 equal to 100 with the series permeance of P5 equal to 4H, as you can see in the complete equivalent circuit here. So from this you can of course have the branch list in a nodal method, how really and all the different branches and different flux. So circuit is described by table, and NPI and NI represent the positive and negative nodes number, and PI the branches of permeance, and FI represents FSI represent the branch with the source like So now starting with the Pn equal to 0, phi n equal to 0 with first branch. So Pn is a 2, minus 2, 2, minus 2 and 2, and phi n is 0, 0. Typically processing the second branch, we get Pn equal to 2, minus 6, minus 2, 6, and phi n 0, 0. And then after processing third and fourth, we get Pn equal to 8, minus 2, 2, minus 2, and 11, phi n equal to 0. And after processing, we get Pn 12, minus 2, minus 2, 11, and phi n we get 400 and 0. So from this now we can find out Pn Fn equal to phi n, and F1 equal to 34.4 ampere, and F2 equal to 6.25 ampere. So using the value of phi for the branch 5, the flux leaving the branch comes out to 62.5 Weber. Now coming to the another method, we call it the mesh analysis for numerical solution of magnetic equivalent circuit. So mesh analysis is based on the application of Kirchhoff's MF law around every independent loop. So that is your summation of all branches FBI minus all branches BI, that is equal to 0. So using a mesh analysis, the system is formed as equivalent to Rn Fn equal to Fn, and where LPJ is the list of all branches for which J H mesh denoted by phi ng enter positive node, and L and J is the list of all the branches for which phi and J enters the negative node. So with the example here, if you look into same kind of equivalent circuit, solve the mesh analysis of the given circuit, determine the flux coming out of the MF, and therein in the two non-zero node potential of 5 branches with the 4 branches of all permeances, PB1 equal to 2 Henry, PB4 4H, PB3 5H, and PB4 6H, and the fifth branch is MF source of FS5 equal to 100 with the permeance of typical P equal to 4H. So after solving, these indices mesh are used for analysis. So positive and negative nodes of each branch also shown. These were selected arbitrarily, and the first step is to analyze in the analysis to establish the branches list, and this is similar to the nodal case. So with the exception of the instead of listing the positive and negative node, the positive and negative mesh list are provided instead. So these are the branches of mesh listed here, and the typically with the all the 5 nodes 1, 2, 3, 4, 5, and so NPI and RBI and FI. So circuit is described by the table, and PI represent the positive and negative numbers, and BI the branch of reluctance, and FEI represent the branch source. So now coming to starting with Rn equal to 0, Fn equal to the first branch, Rn equal to 0.5 minus 0.50, then minus 0.5, 0.00, and 00, Fn equal to 0, 0. And processing second branch, we get Rn equal to 0.75 minus 0.5 minus 0.25, minus 0.5, 0.50, minus 0.250 and 0.25, and F equal to 0, 0. And for after processing third branch, Rn equal to 0.75 minus 0.5, minus 0.25, minus 0.5 element 0.7, and minus 0.2, and then minus 0.25, minus 0.2, and minus 4, Fn equal to 0. And the processing fourth branch, which have a typically Rn equal to 0.75, 0.5, minus 0.5, minus 2.25, and minus 0.5, and 0.867, minus 0.2, and minus 0.25, minus 0.2, and minus 0.5, Fn equal to 0, 0. And then of course finally processing fifth branch, Rn equal to 1 point minus 0.5, minus 0.25, minus 0.5, 0.867, and minus 0.2, and minus 0.25, minus 0.2, and minus 4.5, and F equal to 100, 0, 0. So solving this for Rn, phi n, and Fn, yields phi n equal to 262, 206, and 237 T, and therefore the flux leaving branch 1 is the 262 Weber. So now coming to nonlinearity in the magnetic circuit, which normally in the ferromagnetic part, as you can see here, we have a fringing flux associated with the air gap in the magnetic circuit. The flux line flows into the magnetic circuit, is spread out or frings out into the surrounding medium, as you can see here. So we have a fringing spread out from the air gap to the surrounding medium. Color map shows here the flux density, and of course we have a how the leakage flux is also shown here like. So we can call it here, assuming the flux leaves and enters the core material in normal direction, and fluid flows the path consists of 2 quarter cycle connected by air gap length, and the MF drop by the 2 path is given as MF equal to NA NB H into DL. As you can see here, the fringing and correlation here between the typically how it is passing through the path. So we can call it considering the uniform field intensity. Uniform field intensity along with the path length. Therefore, the field intensity in the direction of path is expressed as H equal to F upon G plus phi R, and B equal to mu 0 F divided by G plus phi r. The fringing flux leaving node A considering the direction of flux is normal to the node surface, and D is equal to L dr is given by the expression. So here phi equal to integral SA B into ds and equal to integral 0 to W mu 0 F upon G plus pi r into L dr, and that is PFA into F like. So you can call it the permeance calculated for fringing flux leaving the node A, and A is associated with the geometry given and can be expressed as PFA equal to phi mu 0 L upon pi logarithmic 1 plus pi upon W upon G, as you can see according to the geometry like. So you can call it permeance of fringing flux, as you can say from the side, associated with the geometry given express PFB equal to 2 mu 0 L upon pi and logarithm 1 plus pi into W upon G. So the reluctance of air gap in the case of U core corresponding to the direct flux path is given Rg equal to G upon WELC into mu 0, and the direct flux path permeance is expressed PGD equal to WELC mu 0 upon G. So you can call it fringing permeance of the outside corner of UI core inductor with the L equal to LC and W equal to minimum of WP into WI into DS plus WB is given by the expression PFOC equal to mu 0 LC upon pi logarithmic of in bracket 1 plus pi upon G and minimum of WI into DS plus WB. The choice of W should be such that it should not exceed the slot width to avoid the overlapping of the node from the other side, and it also should not exceed the slot depth, and W equal to minimum of DS and WS by 2. So the fringing permeance of the inside corner of UI core inductor is given PIC equal to mu 0 LC upon pi of logarithmic 1 plus pi upon 2G and minimum of DS WS by 2, and fringing flux will also occur on the front and back surface of the UI core with the W equal to minimum of WI and DS plus WB and the length L equal to W, and the fringing phase permeance becomes PFF equal to mu 0 WE upon pi logarithmic in bracket 1 plus pi upon G minimum of WI ds plus WB. So parallel permeance like conductance in electrical circuit adds. Thus the total air gap permeance of the UI core inductor expressed as PG equal to PGD plus PFF PIC plus 2 PFF, where the factor of 2 arises because of there is a fringing on both the front and back face of the UI core arrangement, and the reluctance may be calculated Rg equal to 1 upon Pg. So now coming to typically leakage flux in magnetic circuit, the leakage flux refer to flux that is flowing outside of the intended path of in a magnetic circuit. The figure shows the leakage path in UI core inductor, and phi m denotes the magnetizing flux component referred to the magnetizing flux line. So while considering typically the fringing flux component, the flux term considered also comes under the magnetizing flux, and they follow intended path except for the one around the air gap. So the equivalent phi L1 and phi L2 denotes the leakage flux path, and these components of flux never cross the air gap. They are confined to only to typically that part of only. Like so another feature of the leakage flux is that in many situations leakage flux passes through the winding, so that the not all the flux links to all of the turns, and this complicates the calculation of the leakage flux and permeance is typically used to represent the leakage flux. So now energy stored in magnetic linear circuit. Considering the energy stored in magnetic linear inductor having a leakage, having a flux linkage lambda that is proportional to the current and is given lambda equal to Li, because L is the inductance which we can define in terms of, you can call it the linear magnetic circuit. The electrical power flowing into the winding is P equal to Vi, where the V is the voltage across the winding. So now the ohmic drop in the inductor is neglected, therefore the voltage equal to the derivative of the flux linkage resulting in P equal to I d lambda upon dt or Li equal to di upon dt, considering that we have a linear magnetic circuit and we can define lambda equal to Li. So suppose at that time t equal to 0 inductor current is 0, and at the time of t equal to t1 inductor current is I1, the energy that has flown into the inductor and hence the stored in the inductor is expressed as equal to T to 1 equal to P into dt or Li d I to I1 equal to Li di and it equivalent to half Li square in linear magnetic. You can call it expression for stored energy can simply be written in the familiar expression as equal to half Li square or half Pn square Ni square, where the P is the effective permeance of the inductor, and the above equation give the expression for the energy stored in the magnetic linear inductor from a circuit perspective. So now coming to energy stored in magnetic linear system, to obtain the expression for energy stored in an inductor in a field perspective, Ampere law is applied to the geometry shown here in a toroidal geometry. So you can call it a toroid of rectangular cross section that is uniformly wound is considered, assuming that the inner and outer radius are very large and the outer radius is only slightly larger than the inner radius. Applying Ampere's law, we have HL equal to Ni, and where L is the length circumference at means radius and H is the field intensity in the clockwise direction. So, well, we can say the flux total is expressed equal to phi equal to AB, and where is the cross A is the cross section of towed and the flux linkage in is n times the flux. So we can call it therefore the pure lambda equal to NAB, and the power into the core magnetic field is expressed equal to I into d lambda upon dt, HL upon N into Na into dB upon dt, and where P upon V, that is H into d upon dt, where V is the volume of the toroid. So coming to the energy density of the toroid, that is energy per unit volume, is then expressed as E divided by B 0 to T1 H dB upon dt into dt, where the T1 is the arbitrary point in the time, and where E upon B equal to 0 to B1 H into B, B1 is the circumference flux density at the time T1. So assuming a magnetic linear material, so it comes E upon B, that is energy stored per volume, mu 0 to H into H dH, and that becomes the energy density half into mu H square. This is quite famous expression we really use to find out energy density for even utilized for the purpose of designing the machine. So this expression derived for a toroidal geometry with the linear magnetic circuit yields the energy density within the toroid. Now typically, because of the infinitely small amount of the material does not know the geometry in which it is located, so it follows the expression for energy density in applicable for linear magnetic material, with H being the magnitude of the flux field at the some point, and with the magnetic linear material but with statically varying field, the expression that relates the energy stored in the field and geometry equal to half mu V to H square dV. So that comes the total energy stored you can calculate in a volume with the integral of volume. Now coming to slot leakage permeance. So once the component of slot leakage flux is associated with the horizontal flux component level Hx, and the known field components are relevant to UI core, inductor, and many other situations like slot of a motor winding, and applying the Ampere's law to horizontal flux path, we have Hs into Ws equal to Ni dy upon dw into and Ni if y equal to 0 to w and y equal to dw to ds. It depends, I mean, which particular width we are considering out of the two here. So the expression for the field intensity with the mu equal to mu 0 and dv equal to Ws Lc di yields to equal to half 1 by 6 mu 0 dw L upon Ws n square I square plus half mu 0 L upon Ws ds minus dw n square I square. So energy stored by field may be expressed in terms of permeance as equal to half Phs n square I square, where Phs represents the permeance associated with the horizontal slot leakage path. So now coming to, this is about the magnetic equivalent circuit. Now we come to thermal equivalent circuit. Now in thermal equivalent circuit, the process of energy transfer in transformers and electromechanical energy conversion in rotating electrical machines results in I square losses in conductor and core losses in ferromagnetic core, and the heated parts of the electrical machines dissipate heat by the conduction and convection assisted by radiation from the outer surface. And thermal analogies to electrical circuit can be expressed as I equal to I is proportional to Q and V is proportional to theta, where Q is the heat flow and the T referred to the surface temperature. So now coming to mode of heat dissipation, first is the conduction. Conduction, here as you can see in the diagram, the conduction is the energy transfer across the system boundary due to temperature difference by the mechanism of the intermolecular attraction, and the flow of heat by conduction occurs via collisions between the atoms and molecules molecules in the substance and the typically subsequent transfer of kinetic energy. And another mode of heat dissipation is convection. Convection is the heat energy transfer across the system boundary due to a temperature difference by the combined mechanism of intermolecular interaction and the bulk transport. And typically the free, that's a natural, and the forced artificial convection are two convection methods. Right? And third method of heat dissipation is the radiation. So heat transfer involves the transfer of heat by the electromagnetic radiation that arise due to the temperature of the body. Now all aspect with the temperature above absolute zero, radiant energy and no medium is necessary for the radiation to occur. It takes place even in and through a perfect volume. Coming to typically the mode of dissipation, first as a conduction. The conduction, the equation for heat flow between the two surfaces with the temperature θ1 and θ2 separated by heat conduction medium having a thermal resistance R theta equal given is Q conduction equal θ1 minus θ2 divided by R theta, and the unit of heat dissipated by the conduction is in watt, and θ1 and T2 are in degree Celsius, and the thermal resistance R0 is degree Celsius per watt. So typically the thermal resistance is analogous to electrical resistance, and it's something that causes a drop of 1 degree Celsius per watt of heat flow. It can be written R theta equal to rho T upon S or T divided by rho S, where rho is the thermal resistivity of material, typically ohms meter or degree Celsius per millimeter, and sigma is a 1 upon rho, that is thermal conductivity in watt per degree Celsius meter. T is the length of the medium in meter, and is the area of surface separated by the medium, typically meter square. Now coming to thermal capacitance is the capacity of the material to store the heat energy, that is in joules per Kelvin or watt per Kelvin. So it is analogous to electrical capacitance in the context of the electricity and represents the ability of material of a system or to store thermal energy in the form of the heat. And thermal capacitance is the essential parameter in modeling and understanding of the temperature changes in the response to the heat input and removal. Now, this thermal capacitance of an object of material depends on specific heat capacity and its mass, and the formula for thermal capacitance is C theta equal to C into small c into m, where C theta is thermal capacitance in joules per degree Celsius, and the small c is the heat capacity, that is joules per kilogram per degree Celsius, and m is the mass in kilogram. So now coming to typically the mode of heat dissipation through convection, the heat transfer mode between the surface and fluid due to the intermingling of the fluid immediately adjust to the surface of conduction here with the remainder of the fluid due to the fluid motion, and there is a natural convention. The fluid motion due to the buoyancy forces arises from the change in density of the fluid in the vicinity of the surface, and the fourth convection is through fluid motion due to the external force, typically as fan or pump. So we have here the typically natural convection. The heat dissipation per unit surface by natural convection is given by Q small q convention equal to K0 theta minus theta A to power n in watt per meter square, where K0 a constant depends on shape and dimension of the hot body, and n is the constant depends on the shape and dimension of hot body. Its value lie between 1 and 1.25, and theta is the temperature emitting in degree Celsius, and theta A is the temperature of ambient medium degree Celsius. So the heat dissipated per unit volume by convection for n equal to 1. So Q convention is K0 theta E minus theta equal to lambda convention is theta, where lambda convection is the specific heat or emissivity due to convection is given in watt per meter square. So heat dissipated by convection will be Q convection equal to small q convection into S, and lambda Q convection into theta S in watt. So now coming to typically convection is a complicated phenomena, and heat convected depends on various variables such as power density, temperature between heated surface and the coolant, gravitational constant, geometry and orientation of heated surface, thermal resistivity and density, etc. So for vertical planes of heat not less than 1 meter, and with the temperature difference of theta between surface and surrounding pressure, P is the Q convection equal to 2 P to power 0.5 into theta to power 5 by 4, and for vertical tube the Diameter of d meter is a Q convection equal to 1.3 d to power minus 1 by 4 and theta 5 by 4. Coming to now artificial convection, the common method employed for cooling of machine is blasting air on the heated surface. So common formula for air blast or on air surface is lambda dash convection into lambda convection 1 plus kV under root V, where a given watt per meter square degree Celsius square. Lambda convection is a specific heat dissipation of blast surface. Lambda convection is a heat dissipated by natural convection, and V is the relative velocity of cooled surface and air blast in meter per second, and kV is the constant that depends on whether blast is uniform. Now coming to the third mode of heat dissipation, that is radiation. So the heat dissipated by radiation from a surface depends on temperature and its characteristic like cooler, roughness, etc. Considering the case of a very small spherical radius surface inside the large or black spherical cell, heat radiated per unit surface is given by Boltzmann law, that is small q radian equal to 5.7 into 10 power minus 8 E in bracket T to power 4 minus T0 to power 4 in watt per meter square, where T1 and T2 are the absolute temperature of emitting surface and ambient medium relatively in Kelvin, and E is the coefficient of emissivity. And typical example here, you can just see how the heat sink. We have a junction, a thermal material, heat dissipation, and we have a thermal resistance between different junctions like Tj, Tc. Then we have a typically Th and Ta. Thermal equivalent circuit of heat sink surface on PCB is Rj total, resistance is Rjc, then Rch plus Rha, and that is Tj minus Ta upon Q. Now, building a block of the thermal circuit is considering the case of electrical machine. The term L and A represents the thickness and cross section area of the heat sink. T1 minus T2 equal to delta T equal to Q into R as Ohm's law, or equal to L upon lambda A, that is conduction, R equal to L upon Ha, that is convection. Lambda is the heat transfer coefficient and lambda is the thermal conductivity of the conducting medium. So now typically coming to presenting the heat source as a distributed current source, and heat current is generated by every point of the body, and any heat flow encounters the full resistivity of the material, as you can see in this typically diagrams like with the heat dissipation, and then you have a typical equivalent circuit of thermal. And then this is typically the thermal circuit equivalent, the thermal model of electrical machine showing the radial heat flow with the different junction like Ta, Tf, Tsc and TSW and TG, that is air gap. So it comes with the even a capacitive which store the, you can call it the heat energy, typically in stator core and stator winding, and you have a thermal resistance for going to different parts starting from ambient to frame. Then you have a stator core, stator winding, then the air gap. How the really the heat flows from one part to the another, and that how thermal resistance equivalent there of this equivalent circuit of the machine. Now coming to typically electrical machine thermal circuit. As you can see the geometry of this air stator, then rotor, you have air gap in between. So, and how heat flows from the typically from this different parts of this. So, in case of electrical machine, the air gap thermal resistance with the respect to the conduction heat transfer in the radial direction is given by R equal to L upon lambda A by conduction, and L equal to Lg is the air gap length in the meter, lambda is the air thermal conductivity, and A equal to pi dl is the cross section for the heat flow in the radiation direction in the motor, that is surface area at the typically at air gap, D and L are the inner diameter and stator, and core length in the meter respectively. Now coming typically the conduction across slab junction, in many applications we use this kind of the geometry. So the junction T resistance can be represented H like convection, and the junction resistance can be result of weld, bead, air gap or adhesive bond. So T1 minus T2 will be equal to Q bracket L upon K1 1 upon H plus L upon K2 equal to L into 1 upon A. So where the junction is formed by joining the two material of equal thickness L and the different material K1, K2 and of A cross section area. So now coming to the numerical problems. So starting with the numerical one, a composite wall made of two layers, one with the thermal resistance of 0.1 centigrade per watt, another with the thermal resistance of 0.2 watt per Celsius per watt. Calculate the overall thermal resistance of the composite wall. The solution is for a composite wall with the thermal resistance R1 equal to 0.1 Celsius per watt, and the R2 equal to 0.2 centigrade per watt in series. The overall thermal resistance R total is the sum of the two resistance R total equal to R1 plus R2, and that comes 0.3 Celsius per watt. Now coming to numerical problem 2, a magnetic circuit having a pole length of 0.515 meter and the cross-sectional area of 0.002 meter square. If the material has a permeability of 3 pi into 10 power minus 7 Henry per meter, calculate the core reluctance. The core reluctance is R equal to length upon permeability divided by permeability into cross-sectional area, and putting the value, it comes 79,577.47 ampere turns per Weber. So coming to numerical 3, a inductor with a core material of that saturated at 0.4 Tesla has a maximum current of 3 ampere. Calculate the inductance when it operates at maximum current. The inductance is phi upon L. So maximum magnetic flux upon maximum current, that is 0.4 Tesla divided by 3, that is 0.133 Henry or 133 millihenry. Coming to numerical problem 4, heat exchanger with thermal capacitance of 400 joule per Celsius and thermal resistance of 0.004 Celsius per watt is used to cool the fluid, and calculate the final temperature of the fluid after it has been cooled for the 30 minutes with a cooling rate of 50 watt per Celsius. And solution with the heat exchanger thermal resistance heat equal to 400 joules per Celsius, cooling rate is P equal to 50 watt per Celsius, and cooling duration of 30 minutes, that is 1800 seconds, and the final temperature drop can be calculated using the formula delta T equal to P into T upon C0, and then delta T will be calculated by putting this value comes to 25 degrees Celsius. Numerical problem 5, a laptop CPU generates 20 watt of heat and its heat sink has thermal resistance of 0.1 Celsius per watt. Calculate the temperature rise of CPU above the ambient temperature. The solution is with CPU generating 20 watt of heat and a heat sink thermal resistance R theta equal to 0.1 Celsius per watt. The thermal rise above the ambient temperature, calculate delta T equal to Q into R0. So delta T will be 20 watt into 0.1 Celsius per watt, so it will be 2 degrees Celsius. Now numerical problem 6, for the transformer with the primary and secondary inductance of 25 and 22 Henry respectively, calculate the leakage reactance. So leakage reactance equal to L1 plus L2 minus 2M. So we have here 25 plus 22 minus 2 into 7.75, that comes 31.5 Henry. So now numerical problem 7, a ferromagnetic core with relative permeability of 2000 is shown in the figure below. The dimensions are shown in the diagram and the depth of core is 7 centimeter. The air gaps on the left and right side of the core are 0.05 and 0.07 centimeter respectively. If there are 300 turns in the coil wrapped around the central lag of the core, and if the current in the coil is 1 ampere, what is the flux density in the central lag of the core? With these dimensions, so we can calculate with this magnetic equivalent circuit that we have a length of the core reluctance, then the air gap reluctance, and the core reluctance. Then we have other side of reluctance of yoke and the air gap in the yoke, and the MF here with the core length. So we can calculate the reluctance of the typically of the length RL. It is shown in the typically length of the core, then RR, then RC, RS, GL, and then R, and the equivalent resistance typical reluctance equal to REQ, RC plus parallel of RL and RGL, that, and then the flux in central comes phi equal to Ni upon REQ. It comes typically 300 into 1 divided by 123 into 10 to the power 3 Weber. Now numerical problem 8, a copper rod with a length of 2 meters and a cross section area of 0.01 meter square conduct heat. If the rod has a thermal conductivity of 400 watt per meter Celsius, calculate the thermal resistance of a rod. The solution is for copper rod, the thermal conductivity K equal to 400 watt meter Celsius, length is 2 meter, L equal to 2 meter, and cross sectional area and A equal to 0.01 meter square. The thermal resistance R theta can be calculated using the formula R theta equal to L upon mu into A, putting the value in R theta 2 meter divided by 400 meter into 0.01 meter square, so it comes 0.5 Celsius per watt. Numerical problem 9, for the fluid flowing through a pipe, the thermal resistance due to convection is 0.005 Celsius per watt, and the thermal capacitance is 200 joules per Celsius. To calculate the time constant for the pipe when subjected to sudden change in the fluid temperature. So solution is given convection resistance is R theta equal to 0.05 Celsius per watt and thermal capacitance T theta equal to 100 joules per Celsius. The time constant J calculated is tau equal to C theta upon R convection, and putting the value, it comes equal to 4000 seconds or 1 hour and 6 minutes approximately. Now numerical problem typically 10. The copper bar of 12 millimeter in diameter is insulated with 1.5 thickness insulation and having a thermal resistivity of 8 ohm per meter and is kept in the rotor slot of induction motor. Calculate the loss that will pass from the copper bar to the iron of the temperature difference of 25 degrees Celsius to maintain between them, and the length of the bar is 0.2 meter. So the area of insulation in the path of heat flow S equal to periphery of insulation at medium rise into length, that is equal to pi in bracket 12 plus 15 into 10 power minus 3 into 0.2, that comes 8.48 into 10 power minus 3 meter square, and thermal resistance R theta rho T upon S, that comes 1.41 ohm, and heat dissipated can be calculated Q equal to theta 1 minus theta 2 R theta, that comes 17.67 watt. Now numerical problem 11, a field coil has a heat dissipating surface of 0.515 millimeter square and the length of mean turn of 1 meter. It dissipates loss of 150 watt and emissivity of 34 watt per meter square Celsius, and estimate the final steady temperature rise of coil. So final steady temperature theta equal to Q upon SA, that is 150 divided by 0.15 into 34, that comes 29.4 degrees Celsius. Numerical problem 12, the temperature rise of transformer is 25 degrees Celsius after 1 hour and 30.5 degrees Celsius after 2 hours of starting from cold condition. Calculate the heating time constant. So solution, transformer is start from cold condition, therefore its temperature rise given theta equal to theta m in bracket 1 e to power t upon th, and theta equal to 25 degrees Celsius at 1 hour and theta equal to 30.5 degrees Celsius at 2 hours. So then keeping the value in this relation, 25 equal to theta m 1 minus t 2 and 35.7 theta m minus 2 upon th. So this gives heating time constant 1.44 hour. Numerical problem 13, the initial temperature of machine is 40 degrees Celsius. Calculate the temperature of the machine after 1 hour. Its finally steady temperature rise is 80 degrees and the heating time constant 2 hours. Then the ambient temperature is 30 degrees Celsius. The initial temperature rise is theta equal to 40 minus 30, that's 10 degree, and that since theta equal to theta m 1 to t to power minus th upon this, theta I minus theta t upon th, and temperature is after 1 hour is theta equal to 80 in bracket 1 minus e to power minus half plus 10 e to power half, that becomes 37.54 Celsius. So temperature of the machine after 1 hour is 37.54 plus 30, that is 67.54 degrees Celsius. Then we have an unsolved problem, with the question 1, 2, 3, and similarly typically question 7 and 8, and one can solve, and these are the typical references for this material what we have covered with the book of ST Stop or Magnetic Devices Objective Function Approach, ITOPS 2013, and in the other books also. Thank you very much.